Hi, it's me, Dr. Prasad Puthiyillam. Continue my classes for second PU, that is plus 2 chemistry. This is class for unit 2 solutions and it's class number 2. Here I'll be explaining about solution of liquid in liquid, continued by Raoult's law, then ideal and non-ideal solutions, followed by azeotrophs. So vapor pressure of liquid solutions. To explain that in schematic way, I took a container in which two different liquids are considered as component 1 and component 2. So this represents the two type of liquids which forms a liquid layer. So these two liquids are volatile liquids. Volatile liquids means these components or molecules even try to be in gaseous state, not only in liquid state, they try to be in gaseous state. That means they will be converted into gaseous state, means they are volatile in nature. Okay, since they are volatile in nature, let us consider a closed container and the layer which contains more number of molecules, that is liquid layer, and the other above that, that is gaseous layer or gaseous state. Okay, since they are volatile, some of the molecules try to be in gaseous state. The component 1 as well as component 2, both liquids are volatile in nature. And when they are in gaseous state, that will exert a pressure. So those molecules will exert a pressure over the liquid molecule, which we call as the vapor pressure. Okay, so the vapor pressure of component 1 is P1 and vapor pressure of component 2 is P2. So total pressure is P total. And if X1 and X2 represents the mole fractions of component 1 and component 2, we can go to the explanation given by Raoult's law. Raoult's law that was established in the year 1886, or it was published in 1886 by a French chemist, Francois Martin Raoult. He stated that for a solution of volatile liquids, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. If partial pressure is represented by P and mole fraction by X, then simply we can say that P is directly proportional to X. Okay, so here two components are there, 1 and 2, and their partial pressures are P1 and P2, and their mole fractions are X1 and X2. So considering the Raoult's law, we can say that P1 is directly proportional to X1, and this proportionality, if you convert into equality, that means we have to multiply by a constant value, or we can say that P1 is equal to P01 X1. Here P01 is a constant value. Here P01 represents the partial pressure of component 1 if only component 1 was there in this container. That means that is for the pressure exerted by the pure component. Likewise for P2, P2 is directly proportional to X2, or P2 can be equal to P0 to X2. Now, according to Dalton's law of vapor pressures, the total vapor pressure exerted by components will be the sum total of individual components. Okay, therefore P total is equal to P1 plus P2 here. Therefore, we considering that P total is equal to P1 plus P2, substituting the values of P1 and P2. P1 is P01 X1 and P2 is P02 X2. We can rewrite it as P01 X1 plus P02 X2. Now here X1 and X2, if you take the sum total, X1 plus X2 equal to 1. Okay, it may be confusing. That's why I took an example to explain this X1 plus X2 equal to 1, how the sum of mole fractions becomes 1. Consider a mixture of AB. AB mixture contains total of 10 moles, in which A represents 3 moles and B having 7 moles. Therefore, if you calculate the mole fractions, mole fraction is the number of moles divided by total number of moles. Therefore, for component A, mole fraction of A, XA will be equal to 3 upon 10, that is 0.3. Similarly, for B, it will be 7 by 10, that is 0.7. Therefore, if you take the sum total of these two components, mole fraction of these two components, XA plus XB equal to 1. Okay, so I think it is clear now. I took another example. A tertiary system, 3 components are there. ABC mixture. It contains total of 37 moles. in which A is 3, B is 7, and C is 27 moles. So calculate the mole fraction of A, that is 3 upon 37 becomes 0.08. Mole fraction of B, that is 7 upon 37 becomes 0.18918. Mole fraction of C, that is 27 upon 30 becomes 0.72972. Here I took after decimal 5 decimals, 5 points are considered. There are more decimals are there. Therefore, these mole fractions XA, XB, and XC, if you take the sum total, it will be equal to 1. Therefore, it is clear that x1 is plus x2 is equal to 1. Or we can say x1 is equal to 1 minus x2. Okay, so here this value x1 we are going to substitute here. Therefore, it becomes P01 multiplied by 1 minus x2 plus P02 x2. Now rearranging this, it becomes P01 minus P01 x2 plus P02 x2. Okay, therefore P01 minus P01 x2 plus P02 x2. So here x2 is a common factor, and P02 minus P01 we can take out, so we can group them. It becomes P01 plus P02 minus P01 multiplied by x2. So this is the final expression according to by considering Raoult's law as well as Dalton's law to calculate the total vapor pressure of a liquid in liquid solution. From these expressions, we can also conclude that the total vapor pressure over the solution can be related to the mole fraction of any one component. Okay, so here P total is equal to P01 plus P02 minus P01 multiplied by mole fraction of a component 2. Okay, so any one of the component will be related to the total vapor pressure of the liquid mixture. Second conclusion or second point that we can consider from this is total vapor pressure of total vapor pressure over the solution varies linearly with the mole fraction of component 2. That means if component 2 x2 mole fraction, that value increases, P total, that is total vapor pressure, will be increasing. If it decreases linearly, the total vapor pressure also will be decreasing. The third point, depending on the vapor pressure of the pure components 1 and 2, total vapor pressure over the solution decreases or increases. That means P total will increase or decrease with the increase of mole fractions of component 1. That is, if component 1's mole fraction, that is x1, if it increases, the total vapor pressure will be increasing. If this x1 value decreases, then total vapor pressure also will be decreasing. Therefore, the main component, point or main consideration factor is x1 here, as component 1 mole fraction, if it increases or decreases, the total vapor pressure also will be increasing or decreasing. Now, if you consider or plot a graph of vapor pressure versus mole fraction, so vapor pressure is taken in y-axis, mole fraction is values are taken in x-axis, and we are considering component 1 and component 2. First, we will take the example of component 1. Okay, so component 1, its mole fraction, if it is equal to 1, means it is not a liquid mixture, it is a pure component 1's liquid, only liquid 1 is present. Therefore, the pressure exerted by the component will be P01. If I increase the value or decrease the value, so already it is 1, that means further we can decrease only. So if I decrease the value, becomes 0.7, that means another component is present there, whose mole fraction will be 0.3. Okay, so if it decreases, the total pressure exerted by component 1 will be decreasing. Why so? Because we know that P1 is equal to P01 x1. If x1 value decreases, the total pressure exerted by the component 1 also will be decreasing. Therefore, for 0.7, the value is decreased. For 0.5, if x1 equal to 0.5, then further there will be decreasing the value of the pressure exerted by component 1. And if it is 0.3, further decrement in pressure due to component 1. When x1, the mole fraction of component 1 becomes 0, that means that component is not there. That means there is no pressure exerted by that particular component. Therefore, we can draw a trend line like this. So this is the trend line representing the pressure exerted or pressure of that of a component 1. Likewise, for component 2, the second liquid of the liquid-liquid mixture, if its mole fraction value is 0, means it is not there. That means the pressure exerted is 0. On increasing, that is making it as 0.3, that time the component 1 will be 0.7. The pressure due to component 2 will be increasing. Okay, because P2 is equal to P0 to X2, the X2 value is increased here from 0 to 0.3. Therefore, the P2 value for the pressure due to component 2 is increasing. Likewise, for 0.5, the value will be increasing. For 0.7, further increment in pressure due to component 2. And finally, when if it becomes mole fraction equal to 1, that is only component 2 is there, then the pressure due to that particular component is P02. The trend line is given like this. And we can say that from these two behavior, we can say that the total pressure exerted by these two components, that is total pressure P equal to P1 plus P2 or equal to P01 X1 plus P02 X2 will be increasing in this way, or in this trend line represents the total pressure exerted by component 1 as well as component 2. So here the component 1 is considered, the value, its value is considered as lower value than that of component 2, the vapor pressure. That means component 2 is more volatile than that of component 1. Okay, since it is more volatile, then only the value can be given as higher value. Okay, so with that continuation of that, we can also say that the composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the component. That means what is the composition of the components present in the gaseous state, how much composition, how much component 1 or how much component 2 is there, or which type of gaseous molecules are present there, that can be decided or can be determined by the mole fraction of a component 1 as well as a component 2. So that is the meaning of that. So when they are in gaseous state, their mole fractions will not be x1 and x2. That is, when they are going to the liquid state, we call it as x1 and x2. When they are gaseous state, then we have to consider their mole fraction as y1 and y2. Therefore, with the help of Dalton's law, we can say that P1 is equal to y1 P total, or P2 is equal to y2 P total, or we can say that Pi is equal to yi multiplied by P total. Okay, again a confusion may arise, that's why I took an example. Say a mixture of gas, two gases A and B mixture of gas with a total pressure of 1000 torr, and mole fraction of A, that is Ya is 0.25, mole fraction of B, Yb is 0.75. On calculating the partial pressure due to A as per this Dalton's law, Pa is equal to 0.225, that is Ya, multiplied by P total here, that is 1000. It becomes 250 torr. Even for that of B component B, it becomes 750 torr. Therefore, if you consider the total value Pa plus Pb, it becomes 1000, and Ya plus Yb, that becomes 1. That means this expression, this calculation is correct, or we can say that P1 is equal to Y1 plus P total, or P2 is equal to Y2 multiplied by P total, or Pi is equal to Yi P total, Yi multiplied by P total. Since here the Pa and Pb, when we add, we are getting that total value, total pressure 1000. From that we conclude, or we can say that this Dalton's law is true. Okay, this is the simple way to explain that than going for a derivation of that one. So I took this example. Okay, so let us consider one numerical problem based on that expression that we deduced from Raoult's law as well as Dalton's law for vapor pressure of a liquid solution. So an example is given: a chloroform, that is trichloromethane, and dichloromethane CH2Cl2 at 298 Kelvin. The vapor pressures are 200 millimeter of mercury and 415 mm of mercury. Calculate the vapor pressure of this solution prepared by mixing 25.5 gram of trichloromethane or chloroform and 40 grams of dichloromethane at given temperature 298, as well as calculate mole fractions of each component in vapor phase. Okay, so mole fraction in vapor phase, that is Yi. What are the values given? Their P01 values are given 200 and 415 respectively for chloroform and dichloromethane. So let's start, and even the weight is given, mass is given. So if mass is there, we can calculate the molar mass. We can calculate the mole fraction. So molar mass of CHCl3 can be calculated as CHCl3. It consists of one carbon. Carbon atomic mass is 12 and only one carbon, therefore 12 multiplied by 1, plus hydrogen atomic mass is 1 and only one hydrogen is there, therefore 1 into 1, plus chlorine atomic mass is 35.5 multiplied by 3. So multiplying and some adding these values, will be getting 119.5 gram per mole. Similarly, that of dichloromethane will be 12 into 1, hydrogen 1 into 2, and 35 into 2. Totally we will be getting 85 gram per mole. Then moles of CHCl3. Okay, so moles of CHCl3 will be mass by molar mass. That's why we consider these values 25 as well as 40. So 25.5 gram, that is for CHCl3. Therefore 25.5 is the weight for mass divided by its molar mass, that is 119. Value is 0.213 mole. Moles of dichloromethane, that is 40 gram, is the weight of CH2Cl2 or mass of CH2Cl2, divided by 85, it becomes 0.47 mole. Total number of moles, if we calculate, only these two molecules are there. Therefore, total if we calculate, it will be 0.683. Then we can calculate the mole fractions. Mole fractions is the number of moles divided by total number of moles. So number of moles of CHCl3, that is 0.213. Okay, number of moles of CHCl3 we calculate as 0.213 divided by total value, that is 0.683. We are getting a value of 0.312. Here this is considered as x1, since 200 is the lower value is for chloroform. Okay, therefore the component 1 is considered as chloroform. So it is the mole fraction of CHCl3 is considered as x1. The mole fraction of CH2Cl2, that is 0.47 upon 0.683. 0.47 is the moles of CH2Cl2 upon 0.683, that is total number of moles, will be getting 0.688. This value can also be calculated. This is treated as x2. It can also be calculated as 1 minus x1, because we know x1 plus x2 is equal to 1. Then also we'll be getting 1 minus 0.312, that is 0.688. So total vapor pressure of the solution, P total, will be P01 plus P02 minus P01 multiplied by x2. Okay, so P01, that is 200, P02, that is 415, and x2 value is 0.688. On substitution, 200 plus 415 minus 200 multiplied by 0.688, will be getting 347.9 milligram of mercury. That is the total vapor pressure exerted by these gas mixtures. Okay, so now we got P total, and we supposed to calculate mole fractions of components vapor phase, that is Yi. We know that Pi is equal to Yi multiplied by P total. Okay, so for the components, individual components value also we know, even total value also we calculated, therefore easily we can calculate Yi. Okay, therefore we know that P1 is equal to P01 x1. From that, partial pressure due to CHCl3 is P01 200 into 0.312. 312 is the mole fraction of CHCl3. Okay, so substituting that, multiplying these two values, we'll be getting 62.4. Partial pressure exerted due to CH2Cl2, that is 415 multiplied by 0.688. 415 is the value P02. It is given here. Okay, it will be getting 285.5 mm of mercury. Now Pi is equal to Yi P total, or Yi is equal to Pi divided by P total. We calculated the partial pressure of component 1 as well as component 2. Therefore, for those two components, that is trichloromethane as well as dichloromethane, we can calculate its mole fraction in vapor phase. Okay, mole fraction CHCl3 is equal to 62.4 upon 347.9 is equal to 0.18, and mole fraction of dichloromethane is 0.82. Okay, so like that we can calculate the mole fractions for partial pressure by using the equations that we the final expression that we took from Raoult's law as well as Dalton's law for liquid solutions. Further examples will be explained after completing all the classes. At the end, the numerical problems will be discussed. Okay, so here the Raoult's law and Henry's law, a special case, can be considered. Henry's law states that it is relating the partial pressure as well as the solubility, and it says that P is equal to KHX. This is already discussed in previous class. Partial pressure is equal to Henry's constant into mole fraction. And Raoult's law, just now we find out that so we calculated that Raoult's law found it, and now we are getting the expression Pi is equal to P0I Xi. So these two values, these two expressions looks like the same, mole fraction and partial pressure. Only the thing is that the constant value in case of Henry, that is Kh, here it is P0I, that is the ith component's true partial pressure. Therefore, we can say that Kh equal to P0I, which can be considered as a special case. Now, moving on to ideal and non-ideal solutions. Ideal solutions are the solutions which obey Raoult's law over entire range of concentration. Raoult's law says that for component 1, P1 is directly proportional to its mole fraction, and for component 2, directly proportional to its mole fraction. The ideal solutions have two other important properties. The enthalpy of mixing of pure components to form the solution is 0, and the volume of mixing is also 0. That means when two solutions, a solution which is ideal solution, which got prepared by mixing two components or more than two components, more than two liquids, if they mix together, there will be no liberation of heat as well as there is no absorption of heat. That is the meaning of delta H mix H equal to 0. That means those ideal solution, the components, if we mix, there will be no liberation of heat as well as there is no absorption of heat. As well as the change in volume, the delta mix V is equal to 0 means those two components, if you mix, the total volume will be exactly the sum total of the volume of individual components. So we'll move on to its schematic representation. Okay, so let us consider the solution A, the molecule of A, which is one of the component of the solution. So here A and A forms a smooth interaction. AA interaction, that means AA molecules can bond together, intramolecular interactions are possible. And another component is mixed to get an ideal solution. That means component 2 is also mixed to that. They are B type of interactions. These are B molecules. They also can form intramolecular attractive forces will be there. If they can form AB type interactions, okay, so these are AB type interactions. If these molecules form a very good in a good way, AB type interactions are formed, then we can say they are as the ideal solutions. Okay, that means the interaction between AA or AB as well as BB all are almost the same, or it should be exactly the same for ideal solutions. Whereas it is very difficult to get such type of solutions. The interaction of AA, BB as well as AB type interactions can be nearly equal, may not be exactly equal. Therefore, very true ideal solutions are very rare. So we can say that some liquid solutions can be treated as ideal solution because their interactions are nearly equal. Okay, so a perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. They are not exact ideal solution, but we treat them as ideal solutions. Say example, a mixture of normal hexane and normal heptane, and bromoethane and chloroethane, as well as benzene toluene. So these mixtures can be treated as ideal solutions. Non-ideal solution, other than ideal solution, the remaining solutions has to be treated as non-ideal solution, or we can say the solution which does not obey Raoult's law over the entire range of concentration is called non-ideal solutions. So the vapor pressure of such solutions will not be obeying the Raoult's law, therefore it will be either higher or lower than predicted by Raoult's law. If it is higher, then we can say that higher pressure will be liberate, or higher pressure will be present. We can say that positive deviation will be there. If they are lower, that will be negative deviation. Therefore, we'll see the both cases how it happens. So consider a mixture both in liquid state as well as gaseous state. A is the solvent, B is the solute. In this case, what I am giving the explanation. So here AB interactions are weaker than AA and BB. That means the B finds easily to escape to the gaseous state or vaporized state. Here AB interactions, if it is weaker than AA interaction, that means B molecule will try to go to vapor phase. Okay, that is happened here. The B molecules try to be in vapor state, and A molecules are having better interaction than that of AB. So here what happens, than expected from ideal solution, here we can see that it creates a positive deviation. That means the present partial pressure, total partial pressure is higher than that of calculated by Raoult's law. So here green lines represents that of vapor pressure deviation according to or for ideal solutions. Here we find a positive deviation. Such type of molecules having more AA interaction than, or AB interactions are weaker. That means the solute and solvent molecule interaction is weaker than that of a solvent-solvent molecule interaction. It shows positive deviation. Example, ethanol and the acetone mixture. Carbon disulfide in acetone mixture both shows a positive deviation. So two examples given, ethanol and acetone, as well as carbon disulfide and acetone shows positive deviation. Next type of explanation, here A, B type of molecules are there. Solvent molecule is A and B is the solute molecule. In a closed container, there will be a liquid layer as well as gaseous molecules of B is also present. Okay, so on interaction, gaseous molecule means they are in vaporized, so they are volatile liquids. So AB interactions are stronger. AB interactions are stronger. That means than that of AA or BB. That means these molecules from vaporized state or from gaseous state, they try to be in combined state. Okay, therefore less number of vapors present than expected. Here AB type interactions are stronger. Therefore, we can say that this type of molecules, this type of mixtures, non-ideal mixtures, here the theoretically calculated pressure is less because more molecules are going to the liquid state or the mixture state, and the total vapor pressure is decreasing, or there will be a negative deviation. The pressure is decreasing, or we can call it as a negative deviation. So here the green line represents the ideal behavior, and this is the non-ideal with negative deviation, which is the pressure exerted is less. Even the pressure exerted by individual component as well as the total pressure exerted is less than that of the ideal behavior. We call it as non-ideal negative deviation. Say examples, mixture of phenol and aniline. as well as a mixture of chloroform and acetone. Okay, why they form? Because chloroform and acetone example is given here. Chloroform, that is dichloromethane or CHCl2, and acetone, that is CCH3 twice CO, CH3 twice C double bond O. So here C double bond O, here it will be having partial negative charge, carbon partial positive charge, and it can form hydrogen bond with that of hydrogen of chloroform. The oxygen, the ketonic group or the oxygen of the acetone molecule can form a strong interaction with the hydrogen of chloroform. This type of interactions are known as hydrogen bonding. Because of this type of hydrogen bonding, A-B interaction is stronger. Therefore, it shows the negative deviation. We are moving on to the last topic, that is azeotropes. Azeotropes are some interesting examples. They are the binary mixtures having same composition in liquid and vapor phase and try to boil or which will boil at a constant temperature. That means it is a particular composition of mixture in which they try to be together, whether it is liquid state or gaseous or vaporized state. Whether it is liquid state or vaporized state, those two mixtures in a particular composition always try to be in a mixed state. Okay, therefore we call it as azeotropes. Such cases, it is not possible to separate the components by fractional distillation. So in the previous cases, we seen either the positive deviation or negative deviation or even the ideal solutions. We know the vapor pressure of individual components, or vapor pressure means at what temperature it becomes vaporized, at what pressure, what is the pressure, and even we can calculate the temperature. Therefore, by knowing that temperature, particular temperature of that vapor pressure is right, it is easy for a chemist to separate two organic liquids. Okay, that is we called as a fractional distillation or any other methods related to temperature. It is easy to separate than the solution than that of azeotropes, because we know their behavior and we can set the temperature. At the particular temperature, we can collect the gaseous molecule and condense it to get the liquid. Therefore, we can separate two mixtures. Okay, such type of mixtures are formed in industries when they do some chemical reactions, or even in labs. We have to mix some solvents, and some of the solvents after mixing, if we want to separate it for some other application or reuse application, we have to do fractional distillations. In case of azeotropes, the fractional distillation is not possible. We cannot separate them. There may be two types: minimum boiling azeotropes as well as maximum boiling azeotropes. Minimum boiling means their pressure, the temperature or the solution shows large positive deviation. Large positive deviation means from Raoult's law means there will be minimum boiling azeotropes. For example, ethanol water mixture obtained by fermentation of sugar. On fractional distillation gives a maximum purity of ethanol will be 95%. That means on extracting the ethanol or on getting the ethanol, separating ethanol by a fractional distillation, you know why this process is done, mainly to get alcohol. Okay, so while getting that alcohol of ethanol on fractional distillation, the purity of ethanol will not be 100%. It will be maximum 95%, because 95% by volume of ethanol with water is azeotrope. It is an example for azeotrope. So from further 95% of mixture of ethanol water mixture, it is very difficult to separate ethanol. Maximum boiling azeotropes, the last example, last topic. The solution which shows a large negative deviation from Raoult's law forms maximum boiling azeotropes at specific composition. That means example is given: mixture of nitric acid and water. If they are a mixture of 68% nitric acid and 32% water by mass, the boiling point is 393.5. Okay, that means these mixtures, again, it is difficult to separate. They boil at the same temperature, 393.5 Kelvin, is the boiling point of this mixture, and they boil together and becomes gaseous state. On condensing, it becomes a liquid state. It remains in the mixed state. So this is the explanation for Azir. Okay, this is my class for second PU +2 chemistry unit 2. I'll be signing out from this presentation. Thank you very much and have a nice day.